Astronomy Cast, episode 272 for Monday, September 17th, 2012, Abiogenesis. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing good. So once again, as always, we are recording this episode of Astronomy Cast as a live Google Plus Hangout, so you can join us live on the Google Pluses on Monday, noon Pacific, 3 Eastern, 2000 Greenwich Mean Time. 8 p.m. Greenwich Mean Time.
Or at least London time. They're not
London
always
time, yeah. And then join us live, and you can ask us questions, and you can watch us record, and you can see how Pamela uses her hands in the recording to show objects rotating and things flying at the screen. So it's a real treat. And you can also see the episodes on YouTube now as well. So. But it's great to have people join us live. The other thing is we're now doing, I think, 4 different shows every week on Google Plus. So we've got our weekly science hour on Wednesdays. We've got the weekly space hangout on Thursdays. We do our virtual star party on Sunday nights, and then Astronomy Cast on Mondays. So we got lots of great science and space coverage for you. But we've got a new project to mention this week, Pamela.
We do. So over on CosmoQuest, we have what's called Asteroid Mappers, which is a new project that takes data from the Dawn mission, and this is data that is just released, that isn't available in the Planetary Data Center yet, and so you can be among the very first people to look at images of Vesta. And we're working on creating a map of Vesta, mapping out where the craters are, mapping out where the boulders are, trying to figure out where other interesting geological features are. And so if you want to help out with the NASA Dawn mission science team, we invite you to become part of what we're doing over at Asteroid Mappers.
So join us on CosmoQuest, and you can actually help define the craters on Vesta, which the scientists will actually incorporate into their research. So, I mean, that's it. If you ever wanted to contribute to science, now is your chance. That's really cool. And what I love about this is that these are brand new images. I mean, they're not coming from, people haven't mapped these craters or seen them ever before. These are brand new images, raw from the Dawn mission.
At the highest resolution, so we're not downsampling anything or doing anything like that.
Yeah, that's really exciting. Okay, well, let's get on with the show. So the theory of evolution provides a rich explanation for why we see the diversity of life here on Earth. There are so many lines of evidence, from genetic drift to the fossil record. But how did life start? How did things go from a collection of raw materials to the building blocks of life, giving evolution and natural selection a way to take over? That first step from non-life to life is called abiogenesis, and it's one of the most important questions science will answer. And I said will answer because I'm really confident that it will eventually get to the bottom of this.
Yeah, you're more confident on this one than I am.
Really? Okay. Well, we'll see. So the point here is that whenever you have a conversation with a creationist who, they'll go back, they're fine, evolution, fine, fine. I'll give you that we're evolved from monkeys, when really we share a common ancestor with primates. But you take it far back, and then it's like, where did life come from? The theory of evolution can't explain where life came from. Therefore, the theory of evolution is, nonsense.
And the reason I'm doubtful on science solving this one is simply because I'm not convinced that it's a process that happened fast enough to replicate it in a lab given the current funding cycles of things.
So really what we need is more money for science. Is that what you're saying?
Right. And allowing people to apply for funding to do things for many years. The original Miller-Urey experiments, those lasted for a couple of weeks. Then there was one experiment that basically froze a bunch of different chemicals that they thought would lead to life from 1972 through 1997. So that was a nice long baseline, and they were able to see that over this very long period of time, which was short for geology, there were chemical reactions that took place. We're really going to need to have multi-generational experiments to be able to understand all the different possibilities.
Right, but I mean, this is the same argument that's directed at the Big Bang, right? Which is, well, fine, your Big Bang explains the rapid expansion of the universe, the motion of the galaxy speeding away from us, the distribution of hydrogen and helium, the cosmic microwave background radiation, but it doesn't explain what came before the Big Bang. Therefore, the theory is invalid, and that again is
Well,
nonsense thinking, right? Which is
it's
that the Big
they're
Bang.
actually they're different arguments here. So with the Big Bang, we have a theory that we can point to and say our mathematical model creates all these different testable ideas. Let's look at the helium content in non-polluted areas. Let's look at the cosmic microwave background. There's all these different things. The problem is we don't have a theory that is that advanced for the origins of life. We don't know if it formed at volcanic vents. We don't know if it formed in clays. We don't know if it formed in ices. We don't know if it formed at the surface of the water. So these are theories at very different levels of advancement, I guess, for lack of a better phrase.
Right, but I guess my point is that the theory just aims to explain what it aims to explain. It's not trying to explain things that are outside
No, that's true.
of its scope. So, the theory of evolution explains the vast diversity of life forms that we find here on Earth. The Big Bang explains the expansion of the universe. It doesn't explain what came before the Big Bang, and the theory of evolution doesn't explain necessarily where life originated, only the process that we have that's going on all the time. So that's all, and I think that's just really important. Now, and then this additional theory that with evolution that kind of bolts right onto it is to say, okay, abiogenesis. How did you get from the raw materials, carbon, nitrogen, oxygen, etc., into something that could then self-replicate and go from there. So let's kind of take this conversation back to the beginning then. So when did scientists really first start to think about this question?
It actually, in some ways, goes all the way back to Aristotle being wrong in the most amazing ways. So Aristotle, like with so many of the things he put forward, very wrongly assumed that you could think your way into a scientific understanding without actually going out and making any real scientific data, observations, or experiments. And so he, along with many others, thought that life just naturally, spontaneously arose. Leave a piece of meat out and it will spontaneously generate flies. Slime will spontaneously generate frogs. Dead logs in the bottoms of streams will spontaneously generate alligators. And so there was this notion that life just occurs. And it took a while to get past that one. But in a way, it took getting to the notion that, well, there are microorganisms, there are things that we can't see, there are processes that we need to take note of. You can't see with your eyes necessarily that a fly is laying eggs on meat. What you see is a fly on the meat, and then a while later you see maggots, but without the microscope, which didn't come around until the 1600s. You can't get at the fact of, oh, there's eggs I can't see in that meat.
And there's that classic experiment, right? I forget who it was, but they put a piece of meat under a glass jar and no maggots.
There was a whole different series of experiments. Louis Pasteur's were by far the most notable in terms of getting good publicity, where various scientists, Lazario Palazzoni, Francisco Redi, a number of these different individuals demonstrated that if you sterilize something, you don't have the same results. If you isolate something, you don't have the same results. And this was extremely important to making that connection between there are things that happen outside of the visible world, microscopic world, that lead to real world animals that we do see with our eyes. I mean, it's real world in both cases, but I guess visible world critters.
Right. And so, once you I guess, remove the ability for the flies to be able to put in their maggots, then no eggs, no maggots, and the meat
Yeah.
doesn't do what you're expecting. Although it'll still decay, but I mean, this is the
Well,
bacteria that
actually,
got
meat
in there,
won't
right?
decay if you don't have any bacteria. Decay requires bacteria. It'll just get really dry.
Right, right. So there you go. So now clearly there's a source of this stuff. So I would guess fast forward. I mean, then bring on the germ theory. Tremendous advances in microscopes, and then starting with, I guess, in the 1900s, Darwin comes up with the theory of evolution, and you can start to trace things back, but this leads this inevitable question, which
It
is,
was actually in the late 1800s. So we're still looking back even
oh yeah,
further.
sorry, 1800s, yeah, 19th century, yeah, right.
Yeah.
And so Darwin is comes up with the idea of the theory of evolution, but then that leads inexorably to the beginning, which is where did the first creature come from if we're
And
all
and
connected?
and the thing I didn't know until I was researching for the show was it was actually Darwin who put forward the idea that, and this really got to me because this was so early in exploration of electricity, but he put forward the idea that if you mix chemicals, fluids, and electricity, you have basically Frankenstein's recipe for life. And I just love how everything came together so early on, but we're still working to try and figure out how to reproduce this. And it turns out electricity may not be as useful as Frankenstein's story might purport.
Right. Well, but I mean, where was some of the sort of first, thinking or experiments in this process?
Well, the earliest ideas were the hot primordial soup notion that is still, you can't really say there's any leading theories in abiogenesis, but one of the sets of theories is that in the early Earth, where we're still radiating heat left and right, where we're still dealing with a much more active young sun, back in these early days, our extremely hot ocean that would have had a different acidity than it has today, quite possibly could have been a chemical reaction ground. You can't say breeding ground, you have to say reaction ground, for the types of molecules that could eventually somehow make that switch to becoming self-replicating.
And I mean, why is that important? I mean, what is the difference between a jumble of chemicals on the ground and and life, or the building blocks of
Well,
life?
so this is one of those things where there's actually no leading theory. It could have been a puddle on the ground that formed life, but I think the reason that people start off with the primordial soup idea is we've all had that experience of you leave the cup on your table and you have it filled with fluids on a warm summer day, and well, a few warm summer days later you have something really gross. And this
Is
is
it the
science.
primordial soup?
Right,
I'm
right.
gonna
And
make
we've
some.
all
Does
made
anybody want some
jokes.
primordial soup for lunch?
And so when you start to think of a large ocean of all the right chemicals mixing and slushing, and the early Earth was a kind of dramatic place. Back during it's thought that during the first billion years or so, we were periodically getting knocked around by sufficiently large asteroids that they released enough energy to evaporate a large portion of the Earth's oceans, and that would in turn lead to, over time, through the greenhouse effect, the entire ocean evaporating, and only as the planet cooled back down from that asteroid's impact energy would the oceans recondense out of the atmosphere. And so you have this evaporative process that's cycling as we get hit over and over, and all sorts of carnage occurring. And when you think about it, it's like, wow, okay, crazy stuff happening. Life must have emerged from that crazy stuff happening. We don't really have a solid theory, but that sounds good if you're thinking science fiction.
Right, but I know that for example, amino acids are the building blocks of life as we know it. and you can get to amino acids from this primordial soup, right?
Yeah, this is one of the many different ways to get to amino acids. One of
Right.
the things that we're struggling with is it turns out the universe really likes to create amino acids. They're not always stable. Several of them have half-lives of a few years to a few tens of thousands of years, depending on the temperatures of the environment they're in. But we find them in space, we find them on Earth. You can create them in a variety of different ways. The original Miller-Urey experiment was able to create over 20 different amino acids by running all of the chemicals needed to create amino acids through a system that included dotting them with electricity, changing the pressures, and so they just like to form. They're carbon molecules. They do that.
Right, but then as the creationists are so happy to say, getting from amino acids to proteins is a whole other world, right? To DNA, to RNA. So
Well,
what
getting
is thought to be sort of that likely step?
and this is where, again, many different theories. It's some of the ones that we're looking at that I think are the more interesting ones are if you take a volcanic rock and you run fluids through it at high temperatures, it actually creates basically sludge. And the sludge that comes out has molecules that are encased in a chemical membrane. And this starts to resemble cellular organisms. And so perhaps there was some way to get from this membraned molecular sludge eventually to something that was somehow self-replicating. We don't know. But one of the processes that allows us to start to get to something that looks like a cell is lava rock plus water given time and heat equals carbon sludge.
And we've got other, new environments on Earth that have been uncovered, like places like these black smokers at the bottom of the oceans, which are great sources of water and heat and time, right?
Right. So there you won't actually get to sludge because you're completely encased in water. So that's where does it happen quickly at the bottom of the ocean? Does it happen slowly at the surface of the planet? And that actually dictates when life could have started to form. Because if life started to form at the bottom of the ocean, that was a much safer place much earlier than the surface of the planet. So you can actually give life a 500 million year head start by starting it at the bottom of the ocean.
And I mean, what's really always so fascinating is how quickly life got started. I mean, the Earth is 4.5 billion years old, but I mean, we have evidence of life as old as about 500 million years to a billion years after the Earth formed,
we
right?
think that we're finding life, fossilized bacteria basically, from roughly 3.9 to 4.2 billion years ago. Trying to date things is always
Right.
complicated.
But essentially, at the moment after the Earth cooled down to the point that this kind of thing would be possible, life arose.
Yeah,
Yeah.
that's pretty much what we think. And so it's just trying to figure out, well, there's always that possibility that it arose at the bottom of the ocean. It arose on the surface of the planet. We could have had multiple points of origin. So this is where we start looking at extremophiles. This is where we start looking at chemical reactions under a variety of different pressures, under a variety of different lack of liquid. So did life perhaps start in clays where we end up with different mineralogies that start to resemble nanobacteria very closely? It's a fine step between certain microbes. Nanobacteria isn't a microbe. Between minerals and nanobacteria, it's a very fine line occasionally.
But I think one of the other pieces of evidence that we really have is that we appear to be able to trace all life on Earth back to a common ancestor, right? That all life is related. So we don't
all living life.
all living life.
So we have to remember that there's the methanogens, the critters that respirated methane instead of oxygen. That was a completely different tree of life. So it's unclear, did we get from that to this? Did they have a common ancestor, or are they actually two different genesises?
Really? I didn't know that. Yeah, okay. So in other
we
words, there
don't
could.
always have DNA of the oldest bacteria.
Right, of course, yeah. I mean, 4 billion-year-old bacteria in a rock doesn't really tell you much,
Right.
but I guess you can have this situation where if life was super common, then you might see multiple
Yeah.
geneses on Earth. But in this case, it seems like the life that really took off and took over the whole planet does share this common ancestor.
And it's impossible to know though. Was it simply that this life was more efficient and killed off everything else? It's now thought that Homo sapiens, or rather Homo erectus, I'm not sure which, and Neanderthals coexisted, and it's simply we outcompeted. And so we don't know if it was an out competition. We don't know if it was a single origin. And so this is where there's a lot of open questions. And because we have plate tectonics, we can't answer everything.
Yeah, I mean, you can imagine the whole planet being this really fertile environment that life wants to be able to expand into and exploit every single niche once it's got a ready form of energy, and it's got fuel source, it's got things that elements that it can use in its it can consume and get rid of. Then you can imagine it trying to expand into every possible niche on Earth, which it has. It's evolved. And I'm sure it didn't take life that long to expand into every possible niche on the planet in some slime mold kind of bacteria way. And so if you had these two life forms that had started separately running into each other, one probably would have been better equipped to take over those niches than the other.
Yeah, these are the types of things that we're still trying to figure out. We know that we do find life deep in the soils when we're digging for oil. Not we, but when other people are digging for oil. We find it in extremely acidic pools of water. We find it in hot springs. We know that certain critters are resistive to radiation. Some like living in ice. So life has exploited just about every place on the planet Earth that you have a temperature gradient and you have something that can be consumed as a nutrient. So as long as those two things are present, we seem to be finding life.
Now, we're talking about life as we know it, right?
Mm-hmm.
The standard carbon-based life forms with DNA and RNA. Has there been much thought into sort of life as we don't know it?
Well, this is actually a well-timed episode because an article just came out suggesting that we do need to rewrite the tree of life to include some of the macroviruses, that the largest viruses that are out there actually resemble in many ways the most simplistic DNA-based microbes. So perhaps we simply need to start broadening our thought. There are people who consider broadening things out to start including prions, which are basically proteins that affect the brain, as potentially a life form. And then, of course, there are the folks that are trying to do things like replace phosphorus with arsenic, replace carbon with silicon, and look for a parallel way of constructing the chemistry of life by just dropping a row down the periodic table.
And that sounds like it's going to be a pretty fruitful direction to go as well, because we're getting to the point now where, I mean, we're seeing synthetic life forms. I know there was a synthetic virus created just a couple of years ago where they essentially just wrote they used a DNA printer and they printed out the genetic code of it and they injected it into, was it bacteria? And
Yeah.
and boom, you had bacteria, right?
Well,
That
it,
roughly matched the same sort of effect of the actual creature. So we're getting to the point now where with DNA splicing and these kinds of things, you can start to run these experiments. You can kind of go, what if we do this? What if we do that? So
and
yeah.
and it's unclear how fruitful looking for life made out of parallel chemistry is going to be, simply because the energies involved aren't the same, the frequencies of the materials involved aren't the same. But we are getting better at engineering life. From inserting vaccines into potatoes to creating glow-in-the-dark cats to a whole variety of different things. We're changing life, and it's fascinating to see how this is also changing science fiction. There was an excellent book I believe it's called The Wind-Up Girl by Paulo Bagabalu. I can't say his last name. Look up the Hugo Award winners from 2 years ago. And it's a look at a future where we've genetically engineered animals that end up outcompeting the wild ones. And so we end up losing our planet's genetic diversity because we create these things that simply take over. And we see this happening in North America with a lot of invasive species. I know in Europe they're having a lot of problems with mice being an invasive species, porcupines being an invasive species. And it's unclear if we've properly thought through the morals of some of the things we do. There's many nations that are starting to consider, okay, do we need to take a step back from the genetically modified plant species that we're distributing?
Now, one last question then is, there's a lot of news. We've been talking about curiosity quite a bit, and the whole goal here, where curiosity is going to be searching for not necessarily life on Mars, but it's going to be searching for the conditions of life to see if
the chemical precursors.
Yeah, if the conditions were ever present for that life could have arisen on Mars. But we have this problem with panspermia, right? How we've got this situation where even if we do find life on Mars, there's enough rocks traveling between Earth and Mars that if we find life, it might be related to us.
Right. And this is one of those things where it's an open question. Did life on Earth originate on Earth? Did all life on Earth originate on Earth? It could be both. Is the correct answer, and the same is true for Mars. We find rocks on the surface of Earth that came here from Mars when Mars got hit by large asteroids, and the debris actually got put into escape velocity and traveled all the way to Earth. And similarly, Earth over history has been hit by large rocks that have sent things into space. My favorite Scientific American caption of all time was the extinction of the dinosaurs was created by an asteroid that hit, and then in the caption it says sent rocks, debris, and dinosaurs into orbit and beyond. And that would be true. Can you imagine you're the dinosaur there, you're happily munching, you look up, you see something shooting through the atmosphere, and you die, but then you get sent into space as a puddle of biological debris.
Your parts get sent to Mars.
Yes.
To help out the Mars biology, yeah.
Yeah, true.
I know. So do you think that we would ever get to the point maybe where we could start to observe life on other planets using some of the techniques that we're learning here on Earth? Could we, using our telescopes?
Well, I think observing life is a little bit extreme. I think saying that we can observe atmospheres that are out of chemical equilibrium in ways indicative of life is something we can say. We know that oxygen doesn't naturally occur freely, unbound in atmospheres. That needs plants. We know that certain chemicals don't occur in certain ratios in the atmosphere unless you have things like humans with diesel engines. So as we look at other planets, we may see unfortunately, the signs of a polluting industrial economy not too different from our own that is destroying a planetary atmosphere in terms of being in natural chemical equilibrium. So that's what we look for, is things out of equilibrium.
Right. It would suck to be them, but it would be good for science.
Hey, we're there too. We can't really say very much.
They can spot us, so we can spot them.
Yeah.
Very cool. So last thing, and I know this is completely worthless, but why don't let's come up with a prediction here. So I'm a total optimist, and I actually think that science will crack this. Not within the next, I'm going to say decades, 2 decades.
See, I think that we're going to be able to say whether or not life is common by either finding it or not finding it on other rocky bodies in our solar system. I think answering the question of did it originate on land or at sea, Paul Revere had a much easier job than the biologists do.
You want to get to that point where they can just kind of go zap and then boom, there's life, and then zap again, there's life.
And I really think it was probably a process that took so long that there's just not going to be the patience within the funding cycle.
Right, but I love the fact that you were able to sneak in we should fund science advertisement right into this podcast.
Well,
So,
we need to fund things that are longer than 4 years for science.
yeah. All right. Well, wonderful conversation as always, Pamela. Thank you very much for joining me this week, and we'll see you next week.
Thank you. It's been my pleasure. Saving. So don't go anywhere. All we're doing is ending our recordings.
Uh-oh. That's your favorite sound.
And sniffling into the microphone. Sorry, everyone. It's hay fever season. Quite literally, they're harvesting the hay and the corn and the soybeans.
Are they really?
Yeah, and all the fields are getting replaced with ragweed that then springs up to take advantage of the corn not being there.
Just making sure I get the save.
Sorry, this is the paint drying part of the episode.
Yeah. Okay, I saved it. Now I'm going to export it. Okay, I'm safe. I'm safe, but for how long? Okay, so, you know what? Oh, man. Tim Hem just asked a question that I thought was great, which is how much active research is there going on, especially into abiogenesis? And I guess, is there some controversy? And so is that controversy making people not want to go into this area of research?
No, that's not a concern. There's actually a whole lot of people who are studying this, especially through astrobiology funding.
Yeah. Okay, so we'll stick around now for another half hour. So we're glad to answer any questions you might have about space and astronomy. You can post your questions into the event page, or you can post them into the Google Plus page where the recording is being displayed. You can use the hashtag AstronomyCast either on Twitter or on Google Plus, or you can post your question onto YouTube. So, and we'll go from there. So Tom Nath just said finding an Earth fossil on Mars would be bizarre. That would be bizarre, wouldn't it? If there was like a big old dinosaur bone,
Well, finding a big old dinosaur bone, that would be, because most meteorites aren't that big. Admittedly, the Martian atmosphere is much thinner, so it will be far less destructive to incoming rocks. But I think the idea of I don't know if you've ever been to New Mexico, but like Sunspot Observatory, you go walking around the observatory, which is a national park, so you're not allowed to take the fossils away with you. But as you walk around, there's just like rocks, and you look down, and it's like, ooh, leaf. So I can imagine finding meteorite that you break apart, and maybe not leaf, but stuff.
Yeah, actually, you're probably right? That if big enough asteroids have impacted the Earth and blasted solid enough chunks of rock, that there would almost inevitably be fossils that would have made that journey, and then they would have plunked down on the surface of Mars. That would be confusing, I think, if they turned up a leaf or a worm or a fish tooth.
The nice thing about meteorites is they trap within them the atmospheric volatiles that are a signature of what planet they came from. And so you can, through chemical testing, actually figure out where the different rocks originated.
Graham asks, so is there an answer to Sir Fred Hoyle's jumbo jet being built by a tornado in a junkyard? Which, I mean, you've probably, if you've read some evolutionary stuff, this is this comment, which is like, how could life arisen? It would be like a tornado blasting through a junkyard and out coming a jumbo jet. But
see, it actually isn't that big of a step. Literally, you take lava of the right type of lava, like from a cone volcano down in Hawaii, mix it with hot water, and let it just sort of filter through in a hot system, and you start to get naturally forming complicated molecules that have an outer membrane, and it's very similar to the most simplistic bacteria. And as soon as you start being able to form complicated molecules that have skins and other things like that, you can see that this is just a chemical process that organizes things to form lipids, that organizes things to Well, there's lots of different things that we see in molecules, and we know how to recreate them. This is where we're now starting to be able to use 3D printers to create skin.
Yeah.
It's just a chemical process.
Yeah, and it doesn't need to be that complicated, right? All it has to do is make it so that it's a little bit self-replicating. And
Yeah.
that's really all you need, is that something happens that gives that one little molecule or that one little particle a, some way of glomming onto another particle, and
And
then and that's really just kind of it. And
And I
you're
think
not looking
using
for
the word
DNA.
self-replicating is actually part of the controversy. What we need is self-catalyzing. So,
Right.
so it's a chemical reaction that creates what's necessary to keep the chemical reaction going. And once you start looking at it as a ongoing chemical reaction, well, we see stuff like that all of the time.
So Roger asks, how long can a bacteria in so if a large dinosaur travels through space, how long can the bacteria in his stomach survive? So
I suspect that it got thoroughly dehydrated in the process.
right, but the no, but the point. I mean, I guess the point is bacteria is unkillable.
Some of it, yeah.
Some of it is really unkillable, and they actually found there was the the lunar one of the Lunar Explorer mission that was on the surface of the moon, and then in one of the Apollo missions they grabbed it, they grabbed the camera system from it and brought it back to Earth, and in that they found bacteria that they were
Yeah.
able to put in a petri dish and get it going again, and it had been sitting out on the surface of the moon, one of the most inhospitable environments
Yeah.
there are, and it survived.
Well, and
Um,
and archaeologists are forever turning up random ancient glass things filled with wine and preserved food and preserved seeds. And one of the things that I haven't confirmed, but I was told while in Cairo, is that the plant needed to create papyrus had actually pretty much gone extinct for a while, and then they found in the tombs seeds, and so they've started regrowing the plant that's needed to make papyrus scrolls, based on finding seeds that would still germinate.
and then there's of course the water bear,
Yes,
which can't be killed.
no, it's Google water
Yeah.
bear extremophile, and it's this cute little bacteria that has a very long Latin name that begins with a T. And these things have been on heat shields and happily come back to Earth. These things, you can dehydrate them and rehydrate them, and they just go and go and go.
Yeah.
And there's actually a plush version you can get from the microbes
Yeah.
plush microbes company.
My kids love those plush microbes. I got a ton of them around the house here. um, so Tom Nath says, have any biochem experiments that replicate the lipids and other easy stuff have been run for years on end or decades? And I think that's what you're driving at, right? Which is that we go back to that whole jumbo jet in a junkyard concept, that it's all about time. It's about putting all the raw materials together and then just going for time and time and
Right.
time. And so one of these lipid, these experiments you're talking about, really it's just about pushing organic molecules through the muck
Yeah.
for decades on end to see what happens, and then take the end product and then see if you can do something with that. And
Well, and if you're looking at a low probability reaction, you need to allow the chemicals to be mixing and sloshing together for long periods of time to allow the probability to lead to the reaction actually happening.
right, it's very similar to the way they detect neutrinos, right? They have these gigantic vats of water, and then they're looking for just the occasional
Yeah.
zap in there, right? It's about
Or the better analogy is the 20 centimeter hydrogen line that is observed by radio astronomers. This is an extremely rare and improbable spin flip in the hydrogen atom, but because there's so much hydrogen out there, and because it is given the immensity of time over the age of the cosmos, these little hydrogen atoms have time to periodically do that flip that gives off the 20 centimeter line. And so if you leave hydrogen in isolation where no collisions take place long enough, it's given the chance to spin flip.
And we've mentioned this in the past that, if you take large amounts of time, billions of years, hundreds of millions of years, large amounts of space, volume, material, interesting things can happen. Even if it's a super rare event, I'm starting to get convinced by your line of thinking now. Which is, well, it's just that, that it's about having large experiments where you take, billions of tons of this volcanic gloop and just keep looking for certain things to pop out, so that you can then, kindle the fire into the next stage of life. Nicole wants to mention that water bears are actually animals, not bacteria. They
Are
are
they really?
animals. They are
They're an
animals.
extremophile. I have no clue what an extremophile
They are
is in terms
animals,
of
though.
animal versus bacteria.
Yeah, so they're animals, not bacteria, which makes it even more phenomenal how super both adorable and long living. Although you look at them really close under the microscope and they get a lot less adorable looking when you see that kind of their mouth is like this teeth.
It looks kind of like a lamprey mouth.
Like a lamprey, yeah. Like replace a bear's head with a lamprey's head and then you've got,
just the snout part.
Yeah, just the snout. Yeah. So I think that was good. So Ilya Sarah asks, what about, are we just a life form that was created by a previous life form?
We don't know.
We don't know, and I mean that unfortunately just pushes the problem back a step.
Yeah,
So,
then it becomes the movie Prometheus.
Right. Oh, that movie's in a harsh need for a Mystery Science Theater takedown, a riff track. But yeah, right. So I mean, absolutely, and this is one of the theories that where life comes from on Earth, right? Which is the panspermia concept that in fact, life is constantly raining down.
Or the analogy I like is from Men in Black, where they open the locker and there's this entire ecosystem inside of the locker.
Right, but the point being that not only are we getting asteroids from Mars, we're actually getting asteroids from other solar systems.
Yeah.
We're actually probably getting particles. We're probably getting if there's
it's more
life
particles than rocks, but yeah.
Right, but we're possibly getting long-lived bacteria from these other worlds as well. So.
Yeah.
So you can kind of imagine this situation where the moment the Earth cooled down, there's this constant stream of this organic material coming from whole other solar systems, any one of which could contain life. So in fact, one controversial way to think about this is in fact life has been trying to do this for 13 billion years, not just the 4.5 billion years we have here on Earth. So
well, you had to wait for there to be carbon in sufficient densities to I mean that's the thing is the universe did start hydrogen, helium, trace amounts, lithium, beryllium. So you needed to get a few supernovae under your belt before we could get to stars and planets.
But
capable
the point
of
being,
sustaining life.
Right, but the point being that then within the Milky Way, you don't have to just think about the number of times, the amount of volcanic mush interacting here on Earth. Yeah. You actually need to multiply it by the number of stars in the Milky Way, and think about how much time all of those other stars have been pushing volcanic mush through.
And this takes
right?
us to Fermi's paradox: is if life is common, why isn't it visiting? And so that's a completely different show that we've already done. So go listen to that.
We did the first part of it. I actually think, I've done a lot more thinking and reading on Fermi's paradox, and I think there's some pretty interesting sort of responses to it that I'd love to do another show on that.
Okay.
Like the concept of the Great Filter and stuff.
I don't know that one.
The Great Filter? Anyone who doesn't want to be scared can just, end the stream right now. But the idea is that essentially, it's that same concept, right? If you drop a piece of bacteria on a sandwich, then a few days later you're going to have an entire sandwich filled with bacteria. Mm-hmm. So it's that same concept, right? That if life evolves any kind of intelligence, like it's about to, like we have done here on Earth,
mm-hmm.
Maybe we have that we get to a certain point, and life will then start to expand out into the universe, and within a couple of million years, with either our robots or people will have essentially colonize the entire Milky Way. That only takes
Assuming we ever get sufficient budget to do it.
yeah, again, another plug for space for space funding, Pamela. Nicely done. Right, but you get the situation. So in other words, because even if you go 1/10 the speed of light, you create self-replicating probes. You should be able to have fully colonized the entire Milky Way in about 1,000,000 years. So because the Milky Way is 100,000 light years across, so then the question is, we went back to the Fermi paradox, right? Which is, why hasn't it? Why haven't we got life everywhere? And so the concept is, then there must be what's called the great filter. So there must be something that stops life when it reaches a certain level of intelligence from expanding outward and exploring the entire universe, or the entire Milky Way. And so the thought is that it's probably enforced. Whoever got there first now watches all the planets, watches for some event like, I don't know, radio signals or a polluted atmosphere.
So this is a common theme throughout science fiction,
right? And then says, okay, that world over there needs to be wiped clean, so that we can enjoy our monopoly of colonization of the entire Milky Way. And that's called the Great Filter. It's a pretty spooky idea. And there's kind of two filter events, right? One is that life never gets going. We've clearly passed that one.
Yeah.
So the other one then is, life never gets a chance to advance beyond its home system. And that one.
The third is there's that constant background argument that you reach a certain point, and the probability that you're going to get snuffed out by asteroid, disease, or war is sufficiently great that no civilization makes it long enough to actually become intergalactic. So it depends on how much you trust in life to not kill itself.
But again, it comes back to the big numbers, right? Which is that if you have life possibly simultaneously evolving on 4 billion different planets, all you need is 400 million worlds. All you need is just one to decide that it makes sense to colonize the entire Milky Way and then kill all other life. Just one. Right?
And the other option that gets put forward is, what if we're the first planet to have developed a civilization?
Well, what are the chances of 1 in 400 million worlds that we're the first? I don't like those odds. So, like I said, a great filter is a pretty interesting logic puzzle, and it's neat. I was actually having a conversation with somebody the other day, and we were talking about how theoretically in the future, if you can imagine our future, we're going to get to the point where we're going to start to need more and more energy.
Yeah.
And eventually we will go for the most energy we can, which is that we'll enclose the sun in a some kind of sphere, or even turn our sun somehow into a black hole, like collide a bunch more material with it to the point that it turns into a black hole. That
doesn't help matters.
Well, no, but then you can start dropping material into that black hole and siphoning out the energy that comes out in gamma radiation, right?
It still doesn't work that way, but it's a nice fairy tale.
Well, I've heard that it might. That's the most energy efficient way to get matter, to get energy. That you drop matter into a black hole.
But then
piles up the accretion disk.
The amount of energy required to turn our sun into a black hole makes that a useless proposition.
You just collide a few more suns into it. You take 3 or 4 suns that you don't need, collide them all together.
It's more like you take 10 or 11.
Sure, 10, 11, whatever. They've got time.
Minimum. That doesn't
10,
take into
12,
account
whatever.
Things like mass loss through the process.
I'm just saying.
I love it when you throw out science completely.
I'm not throwing out science. Is it impossible to direct the trajectory of a star?
Is it efficient?
No, I'm not saying efficient.
The efficiency.
I'm saying if at the end of the day, if the fuel system works out better, then that's what they'll do. Anyway, the point being that there would be these events, these galactic engineering events that a sufficiently advanced life form would do, and we would be able to spot them. Brian Simpson is mentioning that I'm talking about Dyson spheres. I'm talking about, definitely Dyson spheres, but I'm talking about the next level where you're just you're turning stars into black holes and then using them for energy. But the point is, we would be able to see this because these events would give off a ton of radiation. a Dyson sphere, you would see stars wink out and turn into, I guess, infrared, right? So these kinds of galactic engineering feats, you
But
would
the
spot them.
probability of catching the star actually winking out is sufficiently low that that's unlikely. But
Yeah,
there is a signature in the color of what you'd get from a Dyson sphere, or more likely from a ring world or a series of co-orbiting. I forget what they call them, but instead of having a complete sphere, you have a bunch of small things
right.
orbiting.
Yeah. But the point being that these kinds of events would be uh, visible. And in fact, there actually is a search for Dyson spheres, which I think is
Yeah.
quite amusing. So there are actually astronomers searching through data for Dyson spheres. So, but the fact that we don't see or haven't seen any of these events, again, is sort of an interesting indication.
And something like the Sloan Digital Sky Survey should have started showing these up if they were common.
Exactly, and so that actually starts to bring back that idea that we are the first. We are the first
Or that people found,
civilization.
not people, other civilizations found much more efficient ways than Dyson spheres, which requires you to take a planet and turn it into a spacecraft.
Yeah.
It's easy to imagine that they simply came up with something far more efficient than
Right.
creating a Dyson sphere.
Anyway, we almost just did our sort of part 2 of the Fermi paradox episode right here, but that would be the gist. So if people want to hear that, I would love to have that conversation with you again. So if you want to give us a thumbs up or a thumbs down, let me know in the comments. Thomas is mentioning that energy travels at the speed of light, and then the black hole swallows light and most energy. So Thomas, yeah, no, the trick is that you pile up the material around the black hole so that it can't get in.
Yeah, so to make this clear, Fraser is suggesting that we take a black hole, put an accretion disk around it,
yes,
build a shell around the accretion disk, that somehow
yes.
we're able to get more materials through.
Yeah, and then harvest
and
the gamma
capture
radiation.
the energy from the jets coming off of the accretion disk.
Yeah, that's all. That's all I'm saying. Nothing hard. So Desi Aitken says that it might be feasible to make a micro black hole in a super CERN, which is actually pretty interesting, right?
Right. So this is something I think lots of us are hoping will happen, just so Stephen Hawking can please get his Nobel Prize, please.
Or not happen, because having microscopic black holes
is cool and awesome
cool.
and harmless.
Yeah, okay, fine. Awesome. Yeah, be great.
You want to build spacecraft around stellar mass black holes. I just want a microscopic one. So
I
want to
do lots of stuff. But yeah. Okay, good. We're getting some thumbs up, so that'd be good. Kokute Yori is asking if the universe is self-aware.
We don't know.
Well, but wasn't there a great quote from Carl Sagan, right? Which is that was it intelligent life is the way the universe. I'm totally mangling this, and I apologize. That intelligent life is the way the universe learns about itself, or something like that.
That sounds like a quote I've heard,
Carl
but I don't.
Sagan-y. Yeah, I know. Someone's going to post it in the comments, and then I will take it as my own. So if someone remembers the exact quote.
One of the interesting arguments that leads me to say we don't know is every human body has more cells that are microbes and bacteria and other external living creatures that aren't DNA part of the human being. So there's more of these microbes and bacteria on and inside of your body than actual cells that are produced as part of your growth. And so there's the argument that what if we're just the universe's stomach bacteria, chewing away at the resources on this planet, and that through some we don't understand it form of life, all of these microbes do form a self-aware creature. I don't think this is true, but I'm not going to rule it out because it's a neat idea. So if he's allowed his black holes, I'm allowed my, well, maybe we're just bacteria in a greater scheme of things.
Well, I think I'm running out of questions, so if anyone has a question, we're glad to take it on. Yako Van Shake wants to know, are you sure you two aren't married? Yeah, we are married, just we're not to each other.
We're work spouses.
Yeah. But the cool thing though is we're going to be doing this cruise at the end of the year, and our spouses are going to finally get a chance to hang out, which is great. Actually, I've never met your husband.
No, no, it's most people have never met my husband. It's kind of he's doesn't like humanity. He's a computer programmer.
Jesper
And
Martinson has brought the knowledge. So Carl Sagan said, "We are a way for the cosmos to know itself." So nice and efficient. Thanks, Jesper.
now there was a quantum mechanics theory paper that said we are actually we are actually preventing the universe from collapsing by observing it, because the time that it takes for the wave function of the universe to collapse gets restarted every time we look at the universe. So
Every time
you
we
are
observe
preventing the
it.
universe's collapse.
That's awesome. Cool. All right. Well, I think we've exhausted everybody with our strange directions. So
Yes.
thank you once again to everybody who watched us this week. Now, I know there's a bit of a delay when the episodes of Astronomy Cast kind of make it through the system, but this one will be available on YouTube right away if you want to catch it, as well as the extra banter part. What's up next then? Wednesday, right?
Wednesday is the weekly science hour. I'm going to see if I can get someone to come in and talk to us about asteroids, but I admit I'm still in the planning phases because I spent my weekend programming my brain out. The reason I was programming was the Awingu Sky project. I know what the products are going to be because I'm working on writing the software for them. So if you want to help us fund a project that will gamify space and use all of the proceeds to, not all, but use 50% of all incoming funds or more, so it's a guaranteed 50%, to fund research, exploration, and science education, please go sponsor our Indiegogo campaign. The funding for the
7
Indiegogo
days
campaign,
left?
yeah, 6 days left, I think.
6 days left.
The funding for the Indiegogo campaign goes to pay the stupid things you have to pay for, like business insurance and setting up to be able to take credit card payments and an accountant to make sure we did our taxes right. And setting up an LLC was over $1,000. That really annoyed me.
Done it before. Yeah.
Yeah.
Okay, great. And so, but if you, and also last week, I talked to Emily Lakdawala about Curiosity, and that was a good fun. Emily
Yeah.
is a fount of knowledge and
Yes.
and really knows her Curiosity stuff. And so she was showing all the latest pictures from Curiosity, and you know, me and the folks on the internet were asking her a whole pile of questions. So it was really good. So okay, cool. We'll wrap this up here. So thanks as always, Pamela, and we will see you probably. I won't see you Wednesday, maybe Thursday, if not at the virtual star party. Oh, we're going to be doing some special observing of the moon, I think, on
Yes.
Saturday. So
Saturday,
yeah,
September 22nd is the Global International Observe the Moon Night. So
we got lots
go
of good stuff
celebrate
coming.
the moon.
Yay! All right, we'll see you later, Pamela.
Okay. Bye-bye.
Thanks, everybody.